Welcome to The Deep Dive, the show where we journey into the most fascinating corners of science and technology, untangling complex ideas and bringing you the most important discoveries. Today, we're inviting you to peer into an almost unseen world, the fundamental realm of materials, where tiny particles create truly incredible phenomena. We often take for granted how light interacts with the objects around us, how it's absorbed or reflected or emitted. But, at its core, this interaction is governed by some truly fascinating quantum excitations. Our mission today is to take a deep dive into a groundbreaking discovery outlined in a recent Nature Materials article by Datta and colleagues published just last March. This paper reveals a surprising new way that fundamental excitations in semiconductors, called excitons, can interact with each other. But here's the twist that makes it so remarkable. These interactions are being mediated by a completely different kind of quantum particle, magnons.
And this isn't just about pushing the boundaries of cutting-edge physics for its own sake, although it certainly does that. What's truly significant here is that this discovery is about unlocking entirely new pathways to highly tunable optical devices. Imagine being able to precisely control how a material interacts with light, almost like having a dimmer switch for its optical properties.
A dimmer switch for light-matter interaction.
Exactly. This has massive implications for future technologies, especially as we push the frontiers of computing. It could even pave the way for new forms of quantum technology, like specialized transducers that could link microwave and optical quantum systems, a crucial step towards building complex, robust quantum networks, and maybe even a future quantum internet.
That's a powerful vision, a quantum internet. Wow. But okay, before we get to the truly groundbreaking part, we need to set the stage a bit. So what exactly are these excitons, and how do they usually interact in the materials we're familiar with?
Right, good place to start. Well, at their core, excitons are fundamental excitations that define how semiconductors absorb and emit light. You can think of them as ephemeral, tiny light matter particles. Kind of. When a semiconductor absorbs a photon, a packet of light energy, an electron gets excited, it jumps up to a higher energy state. When that electron jumps, it leaves behind a hole in its original position.
A hole, like a gap?
Exactly, a positively charged gap. Now, this excited electron and the hole, which behaves just like a positively charged particle, are attracted to each other by the fundamental electrical force, the Coulomb force. They form a bound pair, and that bound pair is an exciton.
So if I'm picturing this right, it's almost like the material temporarily creates its own tiny, unstable atom, but made of light and matter. Is that close?
That's a great analogy, actually.
Yeah.
Yeah, and yes, they are absolutely crucial. They're not just some obscure quantum curiosity. Excitons are the driving force behind many emergent phases of matter. They also enable what we call large nonlinear optical responses, which are essential for the next generation of photonic processors we'll need in the future.
Photonic processors, like for light-based computing.
Right, whether for classical computing, thinking about faster, more efficient data centers, or especially for quantum computing. Without a deep understanding of how excitons behave, we simply can't design materials for these advanced applications, let alone manipulate them in new ways.
Makes sense. So once these excitons are created, how do they typically interact with each other in semiconductors? What's their usual dance, as you put it?
Historically, and in most semiconductors, excitons interact through a few well-understood mechanisms. One common one is what we call exchange interactions. These are generally short range, meaning the excitons have to be quite close to each other, almost overlapping. When they interact this way, it often leads to an energy blue shift, essentially, an increase in the excitons' energy.
A blue shift?
Yeah.
So higher energy, like they're repelling each other a bit.
Kinda, yeah. It pushes their collective energy higher. Another prevalent mechanism is phase space filling. Imagine you have a limited number of seats or quantum states available for these electron-hole pairs. As you create more excitons, they start competing for those available states, effectively filling up the available space.
Like musical chairs at the quantum level.
Yeah, something like that. This competition also influences their collective behavior, often leading to a reduction in light absorption. And then you have long-range interactions, like dipolar interactions or even Coulomb interactions. We see these, for example, with tryons, which are charged excitons and exciton that has an extra electron or hole bound to it. These long-range interactions can be more complex, sometimes leading to a blue shift or sometimes a red shift, where the energy decreases, depending on the specific conditions within the material.
So whether it's short-range exchange, phase space filling, or these longer-range interactions with things like tryons, the crucial point in all these conventional scenarios is that the excitons are interacting directly with each other. There's no third party, No intermediary quasi-particle involved in their dance.
Exactly, and this is where our understanding gets a fascinating new layer. The very idea of interactions being mediated by quasiparticles isn't entirely new in physics, mind you. A quasiparticle is essentially an emergent phenomenon that behaves like a particle within a material, even though it's really a collective excitation of many particles.
Like a wave acting like a particle.
Sort of. For instance, phonons are a great example. These are like the quantized vibrations of a crystal lattice, essentially sound waves moving through the material. We've known for decades that phonon-mediated electronic interactions are fundamental to how superconductors work, allowing electrons to pair up and flow without resistance.
Right, the Cooper pairs.
Exactly. Or think about polarons, which are electrons that essentially drag along a distortion in the surrounding lattice, a phenomenon observed in many solar cells, affecting how charges move.
Right, so we're talking about something like a ripple in the material structure, or a specific kind of vibration carrying information or influence between two other particles. It's like a messenger.
Precisely. But here's the novelty that makes this nature materials study so compelling.
Bro.
Quasiparticle-mediated interactions are known in other contexts. The exploration of quasiparticle-mediated exciton interactions is a very new and exciting area of research. There's been some recent work, for example, on phonon-mediated exciton interactions in halide perovskites, which sort of set the stage for this kind of thinking.
Okay, so phonons mediating exciton interactions. That's already pretty novel.
It is. However, what makes this specific study so surprising and significant is the involvement of magnons.
Magnons. Those are magnetic excitations, aren't they? Like the quantum of a spin wave, a ripple in the magnetic order of a material. For someone like me, who might think magnetism and light are completely separate, this sounds, well, wild. How does a magnetic wave even begin to influence how light interacts with a material?
That's a fantastic question, and it gets right to the heart of why this discovery is so important.
Yeah.
You're right. Magnons are quantized magnetic excitations, essentially, waves of collective spin flips in a magnetic material.
Yeah.
Traditionally, they've been considered to operate on vastly different energy scales than excitons, different worlds almost.
Yeah.
They've generally been quite independent of each other in most materials. So their involvement in mediating exciton interactions is not just surprising. It points to a much deeper, more complex, and dare I say, intimate interplay within these materials than we previously understood.
Intimate between light and magnetism.
In a way, yes. It's like finding that a seemingly unrelated third party is actually the matchmaker in a dance you thought only involved two partners.
And that matchmaker has a lot of control over how the dance unfolds.
That's a perfect way to put it, yeah.
So to understand this complex, newly discovered dance, we need to introduce the material that made it all possible. A unique material called CRSBR.
Indeed. CRSBR, or chromium sulfur bromide, is a fascinating material. It belongs to a special class known as magnetic van der Waals VDW semiconductors. To visualize its structure, imagine incredibly thin layers stacked almost like pages in a book. These layers are held together by relatively weak van der Waals forces, along what scientists call the chi axis.
Okay, like graphene or other 2D materials?
Similar concept with the layers, yes. Each individual layer itself has a very specific, somewhat rectangular crystal structure, where you have planes of chromium and sulfur atoms sandwiched between bromine atoms. This gives it a characteristic layered appearance.
And I remember seeing images of its exfoliated flakes. They're often perfectly rectangular, aren't they? That must be a clue to its internal structure.
Absolutely. That distinctive rectangular shape is due to its strong internal crystallographic anisotropy. The atoms are arranged in a way that makes the material much stronger and stiffer in one direction compared to others. So the longer side of these rectangular flakes typically aligns with the material's A-axis. But what really makes CRSBR unique and central to this study is its distinct magnetic identity. Below a certain temperature, known as its Néel temperature, which is about 132 Kelvin in bulk samples, and can go up to around 150 Kelvin in few layer samples, CRSBR exhibits what's called A-type antiferromagnetic AFM ordering.
Can you explain antiferromagnetic ordering simply for us? It sounds complex.
Of course. In a simple sense, imagine each atom in the material has a tiny magnetic moment, like a minuscule compass needle. In a conventional ferromagnet, all these little compass needles would point in the same direction, giving the material an overall magnetic field.
Right, like iron.
Exactly. In an antiferromagnet, it's different. In CRSBR's A-type AFM, the magnetic moments within each layer point in one direction, say, up along the B-axis. But then, in the very next layer, the moments align in the opposite direction, down along the B-axis.
Yeah, so layer by layer, they alternate, up, down, up, down.
Precisely. Successive layers have their spins perfectly anti-aligned. On a macroscopic level, these opposing spins cancel each other out, so the material itself isn't a magnet you can stick to your fridge.
Got it. No fridge magnet.
No. But it has this incredibly intricate and precisely ordered internal magnetic structure. It's like a finely choreographed dance of opposing forces.
And CRSPR also has some really distinctive excitonic features, right?
Yeah.
What makes it stand out from other VDW materials, even beyond its magnetic properties?
That's a critical point. Unlike many other van der Waals materials, CRSPR uniquely maintains what we call a direct band gap.
Which means
It can efficiently absorb and emit light. And it shows strong excitonic photoluminescence, that is, light emission, directly from its excitons, across all thicknesses, even when it's thinned down to just a few atomic layers. It hosts strongly bound excitons with a large oscillator strength, meaning they interact very efficiently with light. This strength even allows for something called self-hybridized polaritons in thicker flakes, where light and matter excitations literally merge into a new kind of quasiparticle.
wow, merging light and matter.
It's pretty wild stuff.
Yeah.
But what's truly fascinating here, and what makes CRSPR a game-changer for this study, is its distinct and well-known feature, a magnetic field-tunable exciting energy. The energy of the excitons in CRSPR isn't fixed. It's directly governed by something quite specific called the canting angle.
The canting angle. What exactly is that, and why does it affect the excitons?
It's a great question, and it's one of the unique properties of CRSPR. Remember how I said the magnetic moments in successive layers are anti-aligned?
Yeah, up and down.
Well, when you apply an external magnetic field to this antiferromagnetic material, those perfectly opposed spins don't just stay rigidly in place. Instead, they start to cant, or tilt, relative to each other.
Tills.
Yeah, like two dancers leaning away from each other but still connected. The canting angle is precisely this angle of tilt between the magnetization vectors of its two antiferromagnetically coupled sublattices. What's special about CRSPR is that this angle of tilt directly influences the electron-hole interaction within the exciton and therefore its energy.
So the magnetic tilt changes how the electron and hole are bound.
Effectively, yes, it changes the electronic environment. And this isn't just theory. Previous studies have shown that if you temporally modulate this canting angle using magnons, those magnetic waves we talked about, it induces oscillations in exciton absorption.
Yeah.
It provides a direct optical pathway to literally see magnon dynamics. So the stage was already set for a very close relationship between excitons and magnons in this material.
Okay, that makes sense. The connection was hinted at before. And the researchers in the study honed in on two specific types of excitons in CRSPR, didn't they? They called them XL and XH.
They did. Through very precise differential reflectivity measurements on an incredibly thin, 3-nanometer thick CRSPR flake at a very cold 5 Kelvin.
3 nanometers. It's ridiculously thin.
It really is.
Yeah.
At that scale, they identified two primary excitons that absorb light very strongly. There's the XL exciton, which is the lower energy exciton, found at one specific energy about 1.36 electron volts. And then there's the XH exciton, the higher energy exciton, observed at a higher energy, around 1.77 eV, as a broader absorption feature. Both of these excitons displayed strong polarization along the material's B-axis, which confirmed that their transition dipole moments, essentially how they interact with light, are predominantly oriented in that particular direction.
And this difference between XL and XH, that turns out to be really important, right?
Incredibly important. It becomes the key to the whole puzzle later on, as you'll see.
Okay, here's where it gets really interesting. So, with all these pieces, the unique magnetic properties, the two distinct excitons, the known coupling between excitons and magnons, how did the researchers actually connect the dots? What was their experimental approach to uncover this new Magnon-mediated interaction?
The team employed a technique called pump power-dependent exciton absorption spectroscopy, specifically using resonant reflectivity experiments. Their goal was to investigate how excitons interact with each other when a lot of them are present, at high densities. Their method involved probing the excitonic absorption while systematically varying the fluence of their laser.
And fluence, in this context, directly correlates with the density of excitons created by their pulsed laser, right? So more fluence means more excitons generated.
Exactly. More juice from the laser, more excitons packed into the material. They used a sophisticated supercontinuum pulsed laser with very short 50 picosecond pulses and a rapid 10 megahertz repetition rate.
Why such short pulses and high repetition?
Well, the short pulses create the excitons quickly, and the high repetition rate gives a strong signal. But critically, this combination was designed to minimize any undesirable heating effects in the sample.
Ah, so they didn't want to just cook the material and see weird effects from that?
Precisely. Heating could mask the true quantum interactions they were trying to observe. They also carefully filtered the laser to specific energy windows, specifically targeting the XL and XH exciton absorption dips they had identified.
Very careful setup. And what was the pivotal observation when they started cranking up that laser fluence? What did they see?
This is where the story gets really compelling. The experiments revealed a large redshift in the XH exciton energy as the fluence, and thus the exciton density, increased.
A red shift. Okay, remind us what that means again.
Right, so a red shift, unlike a blue shift, means the energy decreased. It indicates an attractive interaction between excitons. It's as if the excitons are pulling each other closer, settling into a lower collective energy state, making it easier for new excitons to form.
So more excitons make it easier to create the next exciton, energetically speaking. Attraction.
Exactly. And this redshift was found to be remarkably linear with fluence, especially in mid-range magnetic fields, which is a clear signature of this type of interaction. It strongly suggests a fundamental attractive force at play. Now, here's a crucial contrast that made them scratch their heads initially. The XL exciton, that lower energy one we mentioned earlier.
Yeah.
It exhibited very small fluence-induced shifts across all magnetic fields tested. Almost nothing happened to it.
So XH showed strong attraction, XL showed basically nothing.
Pretty much. This indicated significantly weaker, almost negligible excitant interactions for the XL exciton compared to the XH. This difference was a critical puzzle piece they had to explain. And importantly, they meticulously ruled out any thermal effects by confirming that these redshifts were completely independent of the laser repetition rate.
Meaning it wasn't just the sample getting hot from the laser.
Correct. It was a true electronic and magnetic effect.
That's a very clear observation. One exciton's strongly attracted, the other barely. But then the magnetic field itself played a truly surprising role in all of this, didn't it? That must have been the breakthrough clue.
It absolutely was. This was perhaps the most intriguing finding, a real aha moment. The redshift in the XH exciton energy showed a non-monotonic variation with the magnetic field.
Non-monotonic, meaning it didn't just go steadily up or down.
Exactly. It means the redshift wasn't just steadily increasing or decreasing as they turned up the field. Instead, it was small at zero magnetic field, which is where the material is in its perfect antiferromagnetic AFM state, spins perfectly anti-aligned. But it was also small at high magnetic fields, specifically at or above 2.0 Tesla, where the material enters a ferromagnetic FM state with all its spins perfectly aligned.
So it's small at both extremes of magnetic order, perfectly ordered anti-parallel or perfectly ordered parallel. That's really puzzling. Where was it largest?
The redshift was maximal in intermediate magnetic fields, specifically between 0 and 2.0 Tesla. This is precisely the regime where the applied field begins to disrupt the perfect spin ordering, causing those magnetic sublattices to cant or tilt relative to each other.
Ah, back to the canting angle.
Exactly. This non-monotonic behavior, where the interaction is strongest in the canted magnetic state, strongly suggested that a finite canting angle is absolutely essential for these interactions to be strong. This directly pointed to the vital role of exciton-Magnon coupling, which intensifies as the spin non-collinearity increases. This was the smoking gun, the direct link between the magnetic state and the exciton interaction.
Wow, so the interaction strength mirrors the tiltiness of the magnetic moments. They also explored how the magnetic field generally shifts exciton energies even at low power, just to get a baseline understanding, right?
Yes, exactly. To provide further context, they looked at the overall effect of static magnetic fields on exciton energies using low-power white light, just enough to see the excitons without inducing significant interactions between them. When the magnetic field was applied along the B-axis, which is the easy magnetic axis of CRSBR, meaning it's easier to change the magnetic alignment along this direction, they observed an abrupt shift in exciton energy at a saturation field of 0.4 Tesla.
Relatively low field for saturation there.
Yes. However, when the field was applied along the A and C axes, it required a much stronger field, and the exciton energy shifted gradually until reaching saturation fields of 1.0 Tesla and 2.0 Tesla, respectively. After hitting saturation, the energy remained constant, meaning the spins were fully aligned along the field direction. And here's where that difference between XL and XH excitons becomes even more pronounced. While both excitons showed field-induced energy shifts, the XH exciton exhibited a markedly larger decrease of a full 80 millielectron volts from the AFM to the FM state. That's a big shift.
80 MeV, okay. And the XL.
In stark contrast, the XL exciton only decreased by a mere 15 millielectron volts. Much, much smaller.
Okay, let me try and recap this because it's crucial. The XH exciton, big energy shift with magnetic field, and its attractive interaction with other XH excitons is strongest at intermediate fields where the spins are canted. The XL exciton's small energy shift with field, and its interactions are negligible regardless of the field.
You've got it perfectly.
So that seems like the core mystery here. Why such a dramatic difference between the two excitons, and what explains the magnetic field's peculiar, non-monotonic influence on their interactions? That's the heart of the puzzle they had to solve.
Absolutely. And if we connect this to the bigger picture, the key to understanding the differing behaviors of the XL and XH excitons lies in their fundamental character. Specifically, how spread out or localized they are within the material. The researchers used incredibly advanced theoretical calculations, a technique called an ab initio many-body perturbative approach, QSQ, to gain crucial insights into the microscopic nature of these excitons.
Okay, deep theory dive. What did it reveal?
What they found was fascinating. The XH exciton is described as largely delocalized.
Delocalized meaning spread out.
Exactly, meaning its electron and hole are spread out over a significant area, extending up to approximately 4 nanometers. It also has a predominantly Warnier character. To put that simply, imagine two dancers, an electron and a hole, who are relatively far apart but still connected by an invisible string, moving freely within the semiconductor crystal.
Okay, a loose connection covering some distance.
Right, this spread-out nature makes it very sensitive to the overall electronic structure of the material. Its energy tracks the material's conduction band quite closely. The calculations show that the transition from the antiferromagnetic to the ferromagnetic order reduces the material's band gap by about 0.1 electron volts. And this directly translated to a significant 66 millielectron volt reduction in the XH exciton energy in the theory, which matches nicely with the 80 MeV they measured experimentally.
Ah, so its large size makes it feel the overall magnetic change strongly.
Precisely. Its large, delocalized nature perfectly explained its strong response to the magnetic field.
And the XL exciton is the opposite then, a more tightly bound pair?
Exactly. In contrast, the XL exciton is mostly localized near a single chromium CR site, extending only about 1 nanometer, much smaller. It displays a predominantly Frenkel character.
Protelli. Okay, what's the analogy there?
Think of a Frenkel exciton as those two dancers holding hands tightly, staying confined to a very small area, almost like an excited state within a single atom or molecule. It's much more confined.
Tightly bound, staying put.
Exactly. Because of its Frenkel-like localized nature, its energy shows a weaker dependence on the host band structure. Its behavior is actually quite similar to the well-known light absorption lines observed in materials like ruby, which are explained by what's called ligand field theory, a picture where the excitant's energy is determined by its local atomic environment rather than the overall electronic structure of the entire crystal.
So it cares more about its immediate neighbors than the global magnetic state?
That's a good way to think about it. This fundamentally different character explains why the XL exciton showed a minimal energy change of only 10 MeVs, theoretically, close in the 15 MeVs measured, when transitioning from AFM to FM order, and why it exhibited negligible fluence-dependent shifts. It simply isn't as sensitive to the magnetic order as the more spread-out XH exciton. And this fundamental difference is the critical clue to understanding why only one of them became the star of this new interaction.
Okay, that makes a lot of sense. It's the delocalized, Warnier nature of the XH exciton that makes it so susceptible to the magnetic field, and therefore to these potential Magnon-mediated interactions. How does this theoretical understanding link directly to observations of exciton-magnon coupling? Did they see that coupling?
They did, yes. The theoretical understanding highlights that the dependence of exciton energy on spin alignment directly leads to exciton-magnon coupling. And they actually found direct evidence of this in their experiments. Time-dependent oscillations in the exciton energy were observed at the Magnon frequency, which is approximately 28 gigahertz.
So the excitons were literally wiggling at the same frequency as the magnetic wave.
Exactly. It was literally the excitons wiggling or oscillating in energy in response to the magnetic waves passing through. Crucially, when comparing the two, the XH exciton showed a much larger oscillation amplitude than the XL exciton.
Ah, so the big spread-out one wiggled more.
Yes. This quantitatively confirmed its stronger exciton-magnon coupling, which is perfectly consistent with its larger magnetic field-induced energy shift. The XH exciton was effectively singing along to the magnon's tune much louder. Furthermore, they found that the oscillation amplitude for the XH exciton increased with increasing magnetic field, clearly demonstrating a field-dependent exciton-magnon coupling. This similar non-monotonic field dependence for both the exciton-magnon coupling and the observed excitonic nonlinearity, that fluence-dependent redshift, provided very strong evidence that exciton-magnon coupling is indeed the core mechanism mediating these exciton interactions.
Wow, okay, that's the linchpin. The coupling strength matches the interaction strength, and both depend on the magnetic field in the same weird non-monotonic way.
Precisely. It's the linchpin of the whole discovery.
That's a powerful connection. Experimental observation, theoretical explanation, and a confirmed link to magnons. So they saw it experimentally, and they understood the underlying physics of why these two excitons behave differently. How did they then put it all together into a comprehensive model to explain this Magnon-mediated attraction?
They developed a concise yet powerful model for Magnon-mediated exciton attraction. Let's visualize this again. Under a perpendicular magnetic field, remember, the magnetization vectors of the two sublattices in CRSPR tilt, forming that canting angle.
Right, the tilt.
Now, when excitons, specifically the sensitive XH excitons, are present, their energy also becomes dependent on this canting angle. The core idea is this. As the fluence of the pulse laser increases, elevating the number of excitons, the system itself intelligently readjusts its spin alignment.
Readjust how?
By influencing the Magnon modes. This results in a small, exciton-induced adjustment, a tiny tweak, let's call it, to the canting angle. This adjustment isn't random. It's driven by the system trying to minimize the total energy combining both the magnetic energy and the excitonic contributions.
So the material itself changes its magnetic configuration slightly because of the exciton.
Exactly. It's like the entire material, sensing the presence of more excitons, subtly adjusts its internal magnetic posture to make everyone more comfortable, energetically speaking, to find the lowest possible energy state for the whole system.
Okay. And how does that lead to attraction?
The profound consequence of this readjustment is that the energy difference between states with N excitons and N1 excitons decreases as N increases. Think about the energy needed to add one more exciton. Because the system adjusts the canting angle, when more excitons N are present, the cost of adding that next exciton goes down.
Ah, so adding the next one becomes easier, which looks like attraction.
Precisely. This phenomenon is mathematically equivalent to an attractive exciton interaction. The excitons don't have to directly bump into each other. Instead, their collective presence changes the material's magnetic order via the magnons adjusting the canting angle, which in turn influences how subsequent excitons behave energetically.
So the magnons are the messengers carrying the news. Hey, there are lots of excitons here. Let's adjust the magnetism to make room.
That's a great way to put it, yes. The magnons are essentially the mediators, adjusting the magnetic environment to make the excitons feel attractive forces towards each other. It's a dance where the magnetic background itself is the choreographer, making sure the excite partners are drawn together.
And their model even provided an elegant mathematical framework for this. Expert, without making our head spin with too many variables, what did this equation reveal about why we see this unique behavior, particularly the role of the magnetic field?
That's the beauty of it. The model gave us an elegant equation, A2 is 2U, B sin 2, that captured all the key experimental observations. Let's break down the important parts. The second term, B sin 2, describes the overall shift in exciton energy due to the magnetic field changing the canting angle. This matched the general shifts they measured.
Okay, the baseline shift.
Right. But the third term, Macan 2 into 1, B sin 2, 8, is the crucial one. This quantifies the fluence-dependent shift in exciton energy, the interaction effect.
And what did that term tell them?
It revealed two crucial things immediately. First, it showed that the strength of this interaction is proportional to A squared. Giffair is that maximum energy shift from AFM to FM.
The AEB for XH versus 15 MA for XL.
Exactly. Since the interaction scales with the square of that shift, and XL's shift is about 5 times smaller than XH's, its interaction strength would be 25 times smaller.
Wow. Okay, so that explains why XL's interaction was negligible. The math backs it up completely.
It does. It immediately clarifies the puzzle of the two different excitons. It also showed that for a large number of excitons, N, the shift scales linearly with N, which matches the linear dependence on fluence they saw experimentally. Second, and perhaps most strikingly, look at the sin 2 dependence in that third term. Sine is 0 when the angle is 0 FM state, or AFM state.
Meaning the interaction term disappears at zero field and high field.
Precisely. And sign squared is maximal when E is 2, which corresponds to the maximum canting, the intermediate magnetic field. So the equation perfectly predicted why this interaction peaks when the material's magnetism is in that specific canted state and vanishes at the extremes.
That is beautiful. It matches the non-monotonic behavior perfectly.
It really is. This theoretical prediction perfectly correlated with the experimentally observed non-monotonic dependence of the redshift on the magnetic field. It was a beautiful, satisfying agreement between theory and experiment, a strong confirmation that they were on the right track. Now, while the model is a simplification, it assumes, for example, a single homogeneous Magnon mode rather than the complex reality of many different Magnon modes. Its overall agreement with the observed behavior, particularly that unique magnetic field dependence, provides incredibly strong support for the proposed Magnon-mediated exciton interaction mechanism. It captures the essence of the physics at play.
That's a phenomenal level of detail and corroboration. Theory and experiment singing the same tune. So what does this all mean for the broader world of material physics and, more practically, for future quantum technologies? What's the real so what of this discovery that listeners should carry with them?
Well, I think this represents a new paradigm in material physics, honestly. The large, field-induced exciton energy shift observed in CRSBR stands apart from typical mechanisms seen in other materials, like the Zeeman effect or the diamagnetic effect. Those usually only drive minor energy shifts.
Right, this 80 MeV shift is huge in comparison.
It is. Here, the core insight is that this shift originates from a field-dependent interlayer hopping, meaning how electrons can jump between layers, which is fundamentally governed by the changing canting angle between magnetic sublattices. The profound consequence, as we've discussed, is that in CRSBR, magnons and excitons are no longer independent. There's a true reciprocal influence, a dynamic feedback loop. As the number of excitons increases, the entire magnetic subsystem actually readjusts its spin alignment by influencing the Magnon modes to minimize the overall energy of the system. This adjustment reduces the canting angle, which in turn lowers the average exciton energy, thereby mediating the attractive exciton interaction. It's a sophisticated interplay at the quantum level, where magnetic waves are literally telling light matter particles how to behave.
And this novel interaction has two really critical aspects, don't they? The first is its range. How far can this influence stretch?
Precisely. The unusually large shift in exciton energy observed in this study strongly points towards a long-range interaction. This is a significant departure from more conventional short-range exchange interactions, which require overlapping exciton wave functions to occur.
Like needing to be close enough to whisper versus shouting across a room.
Exactly. Those short-range ones are like whispering. This Magnon-mediated interaction seems to be more like shouting, potentially effective over longer distances. Now, for you, the listener, while other long-range exciton interactions like dipolar ones can be significantly weakened by charge screening in materials.
Screening like other charges getting in the way?
Yeah, essentially neutralizing the long-range electrical forces. The researchers speculate that this Magnon-mediated interaction might be independent of such screening because it works through the magnetic order, not just electric fields. If that's true, it would be a major advantage for practical applications, making it much more robust and effective over longer distances. Of course, more detailed calculations are needed to accurately quantify this range and explore how different Magnon modes and material symmetries contribute. But the potential is enormous.
A long-range, potentially unscreened interaction.
Okay, this raises an important question. If this interaction is mediated by another quasi-particle, what kind of control does that give us?
Right. That brings us to the second critical aspect, unprecedented tunability. You mentioned a hidden knob.
Exactly. Unlike direct exciton interactions, where control over their strength or nature is quite limited, it's just how the excitons inherently interactions mediated by another quasi-particle magnons, in this case, offer a powerful advantage. It provides the tunability of excitonic nonlinearity using external controls, specifically an external magnetic field.
So you can literally dial the interaction strength up or down with a magnet.
That's the idea. Imagine that. You have a precise knob to manipulate the material's optical properties, to dial in exactly how strongly light and matter interact, how attractive those excitons are to each other. This level of precise control is something we simply haven't had for these kinds of fundamental interactions before. It opens up possibilities for devices that can be actively reconfigured on the fly, changing their optical response just by changing the magnetic field.
So this isn't just a fascinating piece of fundamental physics. It has very tangible implications for quantum technologies, which is a field that's moving incredibly fast.
It absolutely does. This study represents a significant step forward in our understanding of exciton interactions in magnetic van der Waals materials. It directly suggests exciting applications in realizing tunable nonlinear optics, which are essential for controlling light in advanced computing and developing new quantum devices. But the most compelling future possibility, and one that really excites the quantum technology community, is the magnonic control of excitonic nonlinearity and its subsequent impact on optical emission. This holds promise for developing quantum transducers, capable of bridging microwaves and optical frequencies.
Okay, quantum transducers. And for someone building a quantum computer or a quantum communication network, why is that bridging so important? What's the bottleneck without it?
Well, imagine trying to connect two different languages without a translator. It's a huge bottleneck. Your quantum computers often speak in microwave frequencies. That's where superconducting qubits, a leading quantum computing technology, operate best. They like the cold, controlled microwave environment.
Okay, microwaves for the computer itself.
Right. But for long-distance quantum communication, sending quantum information securely over networks, we rely on photons, which speak in optical frequencies, like the light in fiber optic cables.
Optics for communication. Makes sense.
Because optical photons can travel across fiber optic cables or even through space without losing their delicate quantum information nearly as easily as microwaves would. Without a really good, efficient translator, a transducer, you can't seamlessly pass that quantum information from your computer, which might be operating on microwaves, to your network, which relies on optics, or vice versa.
So you need a way to convert quantum information between microwave and optical forms without destroying it.
Exactly. And that's incredibly hard to do efficiently. Magnon-mediated exciton interactions, with their potential for strong coupling and tunability, could provide that crucial super-efficient translation service. This mechanism could allow microwave signals, perhaps controlling the magnons, to modulate the optical properties, the excitons, or maybe even optical signals to influence magnons, which then emit microwaves.
So it's a two-way street potentially.
Yeah. Potentially, yes. It enables information to flow freely and reliably across these vastly different quantum domains. It's literally a bridge builder for the quantum future. It allows us to think about truly distributed quantum computing, or a global quantum internet where information can be shared instantly and securely across vast distances. That's a game changer.
It really is. We've seen today how the subtle, surprising interplay between magnetic waves, those elusive magnons, and light-sensitive excitations, the excitons, in a special material called CRSBR, has unveiled a brand new type of attractive interaction. This isn't just a theoretical curiosity, it's a profound demonstration of a finely tuned control mechanism, allowing us to influence how light behaves at a quantum level, essentially using magnetism as our secret ingredient.
That's right. This discovery offers a powerful hidden knob, the external magnetic field, to precisely manipulate how light and matter interact. This opens doors to highly efficient optical devices that can be reconfigured on demand, and fundamentally new ways to engineer materials for the quantum age.
So consider the profound implications of being able to precisely dial in how light interacts with matter using magnetic fields. This isn't just about faster computing or more efficient lasers, it's about crafting entirely new quantum devices, perhaps even enabling that future quantum internet that could revolutionize communication, computing, and sensing as we know it. What other unexpected mediators might we discover lurking in the quantum realm, patiently waiting to unlock even more incredible possibilities for how we interact with and understand the universe around us?